All right, so till now you have seen some embeddings, around 3 or 4 or 5 embeddings. That is nice. That is around the idea of Bourgain. But now I introduce a new kind of embedding, which is based on a combination of ideas in JL Lemma and also Bourgain. I want to introduce some great researchers. All of them are from Israel, and one of them is Yair Bartal. Great articles by Itai Abraham and Ofer Neyman. So they developed very great theories and many nice embeddings, both tree embedding into trees, embedding to LPs, and many different ways for embeddings. So, and many researchers are a student of these people. So also, I should say that in local dimension reduction, isomap, LLE, that today we call it all of these sort of theories, manifold learning. It has applications for protein folding, which is a good application because it is good for humanity. And so you should read an article also about on low-dimensional local embedding. So I want to recall that the Gaussian transform is this, because we need this in this method. And a partition is a collection of disjoint set of clusters C1 through Ct, and such that X is so it covers all X. And when I say P of X, I mean cluster containing X. And the other thing you need to know is that probabilistic partition P hat is a distribution over a set of partitions of X. And also L of X is events that this ball of X, center X, and radius eta delta of Px is inside P of X. And this idea, this embedding, is inspired by Nash method, because he did some embeddings. So he created a randomized Nash device in this article that I'm introducing. And so in random projection, you have seen several times that we use the inner product, but now we use these trigonometric functions sigma omega transpose x, because the inner product of this one is scalar, so we can find the cosine of that, also the sine of that. So we fix this frequency omega. If we fix sigma greater than 0, this is this one that scales everything. And we draw our frequency from normal distribution, but it is u-dimensional distribution. And our claim is that for any x and u in RU, this embedding that I will introduce, which is fx sigma phi of y sigma, and omega is your frequency, is 2 sigma minus 2, 1 minus cosine of sigma x minus 1, x minus y, and The interesting thing is that the expectation of phi of x sigma omega minus phi y sigma omega squared is a GR, that Gaussian transform that I mentioned, of x and y. And R is this one. So these random variables are very concentrated about their expected value. So concentration of several phi correspond to different samples of your frequency omega. It will provide a lower dimensional embedding. So if phi of t of x, if we can define our embeddings by phi of x sigma t omega, and I defined phi that is both cosine and sine, and so theta from x to r 2d because we have 1d for cosine and 1d for sine, so d plus d is 2d. And we arrange those fixed sigmas that I said, that we use it for scaling up to sigma t. It has a lower bound and an upper bound sigma m. And so using these things, I can say that theta x minus theta y, this is another lemma, is bounded by 1 plus epsilon x minus y with probability exceeding 1 minus e to the minus d. So we embedding close neighbors. In embedding close neighbors, x and x and y satisfies x minus y less than equal to delta star of x and y, where delta k of x and y, it means that maximum of delta k and x and delta k and y. So this is just the smallest r that satisfies, subject to ball of x and r is greater than k. The cardinality, it means that you have more than k points in your ball. So if this is an x, you have some points. This is on y, you have some points. You have this nice things. So, but probabilistic partition, you know about probabilistic partition until now, if you have seen my lectures. So if I define locally, I have defined padded partitioning before, but now we have local padded, and so the definition is that let L of x denote the event that ball of x and eta p of x is inside p of x. So for delta inside this interval, p hat is called eta delta locally padded if for any x in x, z is a subset of x excluding that ball which is centered around x. And this 16 delta p of x. And the probability of this event that I said L of x conditioned on L of z, all of them should satisfy z in z is greater than the delta. So for a partition, we define the trigonometric embedding for every for each cluster is different. So because we have many different clusters, and so the embedding, let me show you the embedding, that our embedding is this. First, I have a variable, which is the minimum of the x and x minus x excluding c, and sigma t of x minus y. And now your embedding uses that a. And phi hat is that trigonometric that I introduced. So this one is just sigma t, phi t that you know, which is cosine of that thing, sine of that thing. And why you need this a? This a is, so it rolls off to 0, as you see, near the boundary of each cluster, because the of x and x excluding c is too small near the boundary. And this is, so it is the role of amplitude of the embedding. And we have d clusters, so phi from x to L2, but have 2D dimensions. Phi can be decomposed as, phi can be written as t between d and 1, all of them. So you write it as a vector, long vector. And now the important things, the analysis of this embedding to see what is the distortion, is the distortion good, and those things that we use for all of our embeddings. So the lemma says that let x and y be in x, then if the partition of x is not the partition of y, and so this is the claim 1 of this lemma, then phi of t of x, which is your embedding, preserve the distances up to 2, factor 2. So this is the proof of claim 1 that I want to say. Proof of claim 1. So this is claim 1. We have 4 claims. I prove all of them. First, we observe that for all of x and y, we can say that phi preserve. So by definition, this is until here by definition. By definition, this is just at of x, phi hat t of x, minus at of y, phi hat t of y. Okay, since phi hat t of u, the norm of this is y, then we can write that phi hat of x minus phi hat of y is less than equal to a hat at of x phi hat of x, because this norm is 1, and plus at of y phi hat of y. And I said that this norm is 1 because you know the sine and cosine, so it is obvious why. And then this is bounded by at, so at most we have at of x, at of y. So in the language of computer scientists, we use at most. For claim 1, at of x, so this one, you know, this one, at of x plus at of y is less than equal to d of x and x excluding pt of x plus d of y and x excluding pt and y. And because this one is less than norm of x minus 1 and this one is less than norm of x minus 1, so it becomes, overall, we can say that there are less than 2 times x minus y. And claim 1 false. So if x and y are in different clusters. So claim 2, let me tell you about claim 2. So we proved claim 1. Claim 2 says that now pt of x is again not equal to pt of y, but this time we have more information. We say that the distance between x and x excluding pt of x is greater than 2 sigma t of x minus 1. Then we can say that we can reduce the bound. We can make it tighter. Phi t of x minus phi t of y. Instead of 2 times x minus 1, we have only x minus 1. And I want to prove it. It is very simple, just like claim 1. Now we can say that at of x plus at of y is less than equal to sigma t of x minus 1 plus sigma t of y minus 1. And this is less than equal to 2 max delta t of x minus 1 delta t of y minus 1. And this is less than equal to maximum of d of x and x pt of x and d of y and x excluding pt of y. And this is less than x minus 1, and proof is now complete. So proof of claim 2 is now complete. And finally, we have claim 3 and 4, which says that if now they are in the same partition, because pt of x is equal to pt of y, then we can say that your embedding preserved distances up to this bound, which is bounded by phi t of x minus phi t of y squared. And also claim 4 says that if C is a cluster that has pt of x is equal to pt of y, just like claim 3, then sigma c inverse of that is less than the x and x excluding that partition, and sigma c minus 1 is less than dy and x excluding pt and y. Then we can say that phi t of x minus phi t of y is equal to this phi, trigonometric phi, minus phi t of y. So the proof of claim 3 and 4 is like this. So we define C by pt of x, which is pt of y, so they are in the same cluster. And then we say that phi t of x minus phi t of y, it now becomes at. So different cases, different conditions, different consequences. This is plus at of x, at y times phi hat of t of x minus phi hat of t of y squared. And because this one is now less than sigma c minus 2, and using the fact